Chapter 7, Section 1. We're going to do the central limit theorem for sample means. So essentially, Chapter 6, we were figuring out individual probabilities. You know, what's the probability of finding one of this particular thing that's more or less or equal to this amount within the group. Now we're asking about group sample means, basically. So we're going from individual to a group, essentially. And what is the benefit of this? Well, everything we did in Chapter 6 relies on the fact that the data is actually normal. So if it is normal, you're fine. You know what I'm saying? You can do what we did in Chapter 6 for individual type questions. What's the probability the randomly selected man is, above a certain height or below a certain height? You know what I'm saying? If you do groups or sample means, right? So I take 10 guys, I put them in a sample and average the sample out. I will get the same mean, but the standard deviation will decrease. If I take the sample size to 50 guys, again, the mean will stay the same, but the standard deviation will get smaller. Okay? So in a normal scenario, this doesn't make any difference, right? Because it stays normal either way. You can use the normal distribution functions. However, let's say it's uniform, which means they're all the same. I can't use the normal distribution. However, if I take samples of size 10, right, 10 guys or 10 whatever, each one of these little dots represents 10, right? Then the deviation will shrink down and the mean will stay the same. It's not quite normal, but it's pretty close. If I increase the sample size 50, then it really does become normal, but the standard deviation shrinks in even more. So even if I have a U-shaped distribution, right, if I keep increasing the sample size, it becomes more and more normal. The only thing it differs is the deviation is going to get smaller, essentially. Then I can use the normal distribution. Okay? All right, so that's the general idea of the central limit theorem, is you're using the distribution of sampling means. Each one is a sample of means, basically. So you take a mean of each sample, right, and the distribution of that. So that becomes a sampling error, not standard deviation, essentially. So when you take the standard deviation divided by the square root of n, that's the standard error, or SE, essentially. So that's why the standard deviation gets smaller. It's getting smaller by the square root of n, essentially. So the whole distribution. However, the mean of the sample, right, the mean of the sample, right, is the same as the mean of the population. That doesn't change. You also need to modify the z-score to account for that sample size. Other than that, everything else is the same. Okay, so if you want another video on standard deviation versus standard error, there's a little video right there, basically. So we did standard deviation before for single data. Now these group means, we do standard error, essentially. Okay, so let's do a very basic example of why this works. So let's say I take quizzes from 4 kids. I have a 2, a 6, a 4, and an 8 as the scores, correct? If I graph it, this is not normal. This is a uniform histogram. So I graphed it. It's not normal, which means I can't do any of my normal distribution stuff. All right, let's take the mean of this, right? So that's 2 plus 6 plus 4 plus 8 divided by 4, right? And that's going to be 20 divided by 4, which is 5, right? So the average score for these 4 kids is a 5, essentially, right? Okay, so that is the population mean. Notice it's a mu there, population mean. All right, so if I do the standard deviation, what's that going to be? So that's going to be the square root of, a long square root, right? 2 minus 5, right? Squared plus, right? Because you have 2 minus 5, 6 minus 5, right? Squared, all divided by 4, right? And then you have to do 4, then you have to do 8, correct? So to do all 4 of them. Okay, so if I do that, I will get the square root of 20 over 2, essentially, or if I simplify, I get the square root of 5, right? Okay, so that is my mean and standard deviation of the population. The problem is I can't do any of the stuff from Chapter 6 doing normal distribution calculations because this is not normal to begin with, right? Okay, so let's do samples of size 2. So if I do samples of size 2, the smallest sample I can get is a 2 and a 2, right? Sample twice, I get a 2 and a 2. The largest sample I can get is an 8 and an 8. Okay, and then we do all the combinations in between, right? So 2 and 4, 2 and 6, 2 and 8, right? 4 and 2, 4 and 4, 4 and 6, 4 and 8, 6 and 2, 6 and 4, 6 and 6, 6 and 8, 8 and 2, 8 and 4, 8 and 6. So if I do the mean of the samples, right, so the 2 and 2 average is 2. 2 and 4, the average is 3, right, because 2 plus 4 is 6, divided by 2 is 3, right? 2 plus 6 is 8, divided by 2 is 4, and then 2 plus 8 is 10, divided by 2 is 5, right? So if I go through and figure out all the sample means, I will get these following numbers. Right? So the mean of this sample is 7, right? Because 8 plus 6 is 14, so the average is 7 essentially, right? Okay, so let's take the mean of the sample. Oh, there should be a little X bar above it, right? Let's put the little X bar. Come on. There we go. Okay, so the mean of the samples. Sorry, if I add all up these samples, right? So I have 2 plus 3 plus 4 plus dot 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 all the way to 8, right? Because I have 2, 3, 4, 5, all the way to 8, right? And there's 16 of them, right? Because we got 4, 4, 4, and 4, right? So if I add up all of these numbers, I'll get 80 divided by 16, which is 5. Wait a minute, that worked out perfectly because that was also 5. But that's what we thought though, right? Because if you do sample means, right, the population mean and the sample mean stay the same, right? So the center of the data stayed the same, okay? But this should get smaller, right? The standard deviation, when I convert to standard error, should get smaller, right? So let's take all of these and convert them down to here. So the smallest mean I can get is a 2, right? Right? The largest mean I can get is an 8. Okay, because these are all a mean, right? Sample mean, correct? Because X bar is sample mean, correct? Because mu is population. That's the population of samples. Okay, so 3, 4, 5, 6, 7, and 8. All right, well, there's only one way to get a 2 and one way to get an 8. There is 2 ways to get a 3. Right? There are 3 ways to get a 4. Right? There are 4 ways. Nope, I did that wrong. That's 2. That's 3. That's 4. Right? And then 6 is 3. Right? There's 6 3s. Or 3 6s rather. There's 2 7s, right? Okay, so if we fill that box in there, we're going to get this right here. Okay, right? Because if you look, there's 5. Oop, I copied the wrong numbers. That's not right. There we go. That worked out good now. Okay. I copied the left one twice. Okay, so if I look here, I have 4 5s, don't I? I have 4 5s. Correct. I only got 3 6s. Right? Got 3 6s. Right? Because these are all the sample means. And notice what happened. If I graph it, now all of a sudden it's actually normal. Right? This is why the central limit theorem works. Was it normal to begin with? No. So the original data was not normal, but if I made sample means out of it, it becomes normal, right? So if I go through and do all the math here, right, take all of these, right, so that's 2 minus 5 squared, right, plus dot dot dot, right, 8 minus 5 squared, right, because there's 16 of these, right? Right, there's 1 2, there's 1 8, there's 2 3s, there's 2 7s, so do this 16 times, right? right? So sample mean, right, minus mu, which is 5, square it, add it up, do it 16 times, right? You will get, right, 40 over 16, right, which you simplify, that's 5 over 2, so I get root 5 over root 2. You're like, that looks kind of familiar there. What's going on there? Well, if you think about it, right, what just happened? Let's just take this part here, copy, and paste. Whoops. We gotta go to math type. I did that wrong. Math type. Nope. There we go. Right? That's what happened, right? So you take the population standard deviation, which we got was root 5, and you divide it by the square root of sample size, and wait a minute, that gave us the standard error, which we had before, right? And these should have little bars above them. That should have a little bar above it. Nope, that's not quite right. Let's put that little bar. There we go. That's the standard error, or the standard deviation of the sample means, essentially. There we go. Okay, so let's look here. The mean was 5, population mean. The mean of the samples was 5. The standard deviation of the samples is root 5. The standard error of the sample means is the same thing divided by square root of 2, which is the sample size. So it got smaller, which is what we thought. So the standard deviation got smaller, but the mean stayed the same, right? So long story short, right? The mean of the population is 5. The sample mean is 5. Root 5 over root 2, right? Or root 5 over root 2. Okay? Same thing, essentially, correct? All right, and this is the mean of the sample size. This is the mean of the sample. Samples, rather. Okay, all right, that's the end of the first video.